For example, when has both a speed and a direction. So when would be an example of a vector? Something that to fully describe it, we need both a number and a direction, or a speed and a direction. Unlike temperature, where fully describe temperature, all we need is just a number. Fully describe mass, all we need is just a number. But items that some items can only be described with both a number and a direction, and these are called vectors. So the topics for this chapter are vectors, properties of vectors, coordinate system and vector components, and vector algebra. This chapter is basically just all about how to add vectors, which it's key for your success in this class that you get this information in this chapter. Not only for this class, but for the class after this one, if you guys take 1151. If you don't understand how to do vector addition and break vectors down into components, it's going to cause you a headache for the next year. So I really urge you, if you struggle with this material, get with me, get with people in the help room, get with whoever, your math professor, whoever you need to get with, so that you can get yourself squared away on this material, so that you don't end up struggling with math instead of struggling maybe just a little bit with physics. Not that I want you to struggle with either, but if we're going to struggle with something in this class, I would rather do physics than math. So I'm actually going to do a reading quiz today to see how well prepared we are. So first question, what is a vector? Whoops. Okay, stop this at 35 seconds or so. I think 49 is our cap for the day. And what we'll see here is that a vector is a quantity having both size and direction. And the class primarily got that. But yes, that is the correct answer. Some of the other answers are I could easily see how you can get confused about it. But in this case, we're looking for just a definition of what a vector is. And that's a quantity having both size and direction. So let me proceed on here. Question number 2. What is the name of the quantity represented as this symbol up here that we have? Your performance today will not have any ill bearing on your grade at all, so you can put that little concern to rest if you all have concern about that. Shut this down. Thank you. Let's see. And in this case, it's a unit vector in the x direction. Okay. And this is something that... so this is a nice piece of information for me. This lets me know where you guys are. And this is something, check marks off. So I see the check marks off. The correct answer is D here, unit vector in x direction. For whatever reason, the check marks off. But we will get into that in a little bit, probably tomorrow, actually. Last question. This chapter shows how vectors can be added using what? Who's lying out there? There we go. See that? That's the nice thing. I didn't make comments like that without actually calling anybody out in the class. So we're all anonymous. And whoever that person was, I was just playing around. I'm sorry. So we got mixtures of V and E here. The correct answer, as we'll soon find, is that this chapter shows how to add vectors using both graphical and algebraic addition. So now that I know, again, where we all stand, well, we'll skip this one. We can go on and start through with our material here. This slide should look very familiar to you. You guys have seen it before from chapter 1. Just talking about the difference between vectors and scalars. So again, our scalar is just a physical quantity that can be described by a number alone. And when we say a number alone, we of course are including units in that. So when we say the temperature is 32, what? 32 degrees Fahrenheit, 32 Celsius, 32 Kelvin. Huge difference. So we always have to, of course, include units when we're describing a physical quantity. Otherwise, our answer is not complete and it doesn't make sense. Mass and temperature are both examples of scalars. Vectors, again, this is a physical quantity that needs to be described by both a number and direction. And we've already dealt with position and velocity and acceleration. We'll see force as well, and each of these is going to be basically our key vectors for this particular class. Position, velocity, acceleration, and force. And we also make the note that a magnitude of a vector cannot be negative. So whenever we talk about the size of a vector, this is always a positive quantity. Even when a vector, for instance, is pointed down our negative x-axis, we still say, well, this vector has, for instance, 20 meters per second in the negative x direction. So our magnitude in that case is 20 meters per second, and our direction is the negative x direction. So when we talk about vectors, two items again, both the magnitude of our vector and the direction of our vector. So when we draw vectors, our vector here is a representation of the speed at this instant, or at this point right here. So at this point in this object's motion, it's moving 5 meters per second in that direction. So we stick a tail at that point to represent exactly how fast, to represent the velocity at this particular position of our item. And of course, the length of our vector is related to just the magnitude that we have. The larger the magnitude, the longer the vector we're going to draw. So again, just to beat a dead horse. The vector is drawn across the page, but it represents the particle's velocity at this one point. Okay, slide 15 here. This is a representation of displacement. So what did we say displacement was? Can somebody tell me in words what displacement is? Yeah, difference between final and initial position. Displacement. I kind of really like this definition from your text, so I stole it. So this is just a straight line connection between initial and final positions. In other words, I could be moving around, maybe walking back and forth in the classroom as I do. But my path could look something like this and wander all over the place. But my actual displacement is just a vector drawn from my initial position to my final position out here. So this is my path, but this vector right here is my displacement. So path and displacement are not the same things. Displacement is just basically the vector drawn from our initial position to our final position. Let's see here. In this particular example that I've got up on the screen, we've got a person that starts out at point P and walks 4 miles in the x direction, and then walks 3 miles in the y direction, or we can say 4 miles east and 3 miles north. And then we're asked to find what is the net displacement. And again, it's just a unit vector drawn from the starting position to our ending position out there. And we can also see, and we remember from chapter 1, that when we draw these legs out, say our 4 miles to the east would be vector A, our 3 miles to the north would be vector B, and then our resultant vector, our net displacement, is just the graphical addition of vector A plus vector B. So C equals A plus B here. And we went through the rules for vector addition in chapter 1 for graphical addition here. So given vector A and vector B, we're going to draw A. We're going to draw B so that the tail of B is at the tip of A. So we first draw A, then we draw B so that the tail of B is at the tip of A. And then we draw a vector connecting the tail of A to the tip of B. So this vector here connecting the tail of A to the tip of B is vector A plus B. Take a look at maybe an example to put some numbers in and make this kind of concrete for you. We've got a situation where somebody's going to walk northeast for 20 feet, then walk north for 20 feet. And my question here is, well, what is our displacement? So, first thing to do, what do I do here? Thank you, yeah. Eventually you guys are going to get bored of that question. You probably already are, and maybe I'll stop asking it. But it's an important point to hammer home. Instead of X and Y, I better make this east and north. So, our person walks 20 feet northeast. If this is 20 feet northeast, we know that this angle here is 45 degrees, right? Put a little arrow there, and they're going to walk north 20 feet. Okay. So this would be, say, leg A, leg B, and then the question is, what is the displacement? So now we need to just draw a vector from our initial starting position to our ending position. Basically like that. And we're going to call this vector C here. Okay? So I've drawn my picture. Now, if I actually want to assign numbers here, I'm given numbers in the problem, 20 feet, 20 feet. I'm given directions. So I would like to be able to actually specifically spell out a number of the magnitude of C and give some angle of what direction it's pointed in. Go ahead.
Could you solve being 45 degrees and 20 feet south of the distance traveled east and the distance traveled north?
Yeah, that's certainly one way to do it. Yeah. And that may actually be the easiest way, and we'll get to that later on in the chapter. But for right now, we're going to stick with the graphical addition. But yes, that's a great answer. So, we've got an angle here that's 45 degrees. Have you guys ever heard of the law of cosines? Maybe back, it's been a while maybe. But our law of cosines says that when we've got some triangle, and I better define my triangle here, say, for the general case where we've got A, B, and C, and this is my angle theta, I can say that this law of cosines can help me to find one of these particular items if I know the other three. So in this case, as I look at the triangle I've drawn over here, I know the magnitude of A, it's 20 feet. I know the magnitude of B, that's also 20 feet. The thing I don't know right now is any of these three angles. So how do I get there? What can I do?
The angle between the first leg and the second leg will be 181.5.
Yes, thank you, yeah. So, I can draw a straight line in right here. That's horizontal to my east axis. When I have two lines that are parallel, I know that this angle and this angle are going to be the same. This is a rule from geometry. So this is also going to be 45 degrees right there. 45 degrees right there. And we said that this is due north. My line here that I've drawn is parallel to my east-west direction. So this is going to be a 90-degree angle right here. So this tells me that this entire angle is 135 degrees. And at this point, I need to redraw my sketch because it's beginning to get a little cluttered. I said that this angle right here is now 135 degrees. This is my vector A, my vector B, and my vector C. Well, now I can just use my law of cosines. I can use my law of cosines to find out the magnitude of C here. So, C squared equals A squared plus B squared minus 2AB. Cosine theta, I just need to fill in some numbers. My magnitude of A is equal to 20 feet. My magnitude of B is equal to 20 feet. So let me fill in numbers here. C squared is equal to 20 feet squared plus 20 feet squared minus 2 times 20 feet times 20 feet times my cosine of 135 degrees. And so I've got all numbers over here. This is 20 feet, 20 feet. That may not be that clear. But all I need to do is just plug this into my calculator and go. And take the square root of C squared, and I end up with my C is equal to 37 feet. Right about 36.9, something like this. Good enough for what we're doing right now. Especially considering the fact that we really, I've only spelled out one significant figure, but we'll say that I've actually used it. So C is equal to 37 feet. So this is my full answer or not? No, of course not, because we're talking about vectors, right? You don't just need a magnitude, we need a direction as well. So now I need to be a little bit more specific about, say, some reference frame that I'm talking about. I can't just give an angle, I need to give an angle with a reference frame. So in this case, east, north, we're going to say that our reference frame here is the east axis. Okay? And we're going to assign this to be angle alpha. Now, one thing here, we know that this particular angle right here is 45 degrees. We were given that in the problem statement. And I'm going to call this angle right here beta. And this will tell me that my alpha is equal to beta plus 45 degrees. So now I need to find beta. This is just another application of the law of cosines again. So in this case, let me redraw my triangle one more time. And you notice, I mean, this is something that you should do too. Whenever a problem starts to get confusing, go back and look at your sketch and redraw. Just continue to redraw. John.
Since you don't really use law of cosines, do you, since A and B are the same length, therefore you can just take 180 and subtract 135 divide by 2. Right?
Is that correct?
That's not something that's trying.
Yeah, you're right. For the sake of my, I'm going to do it anyway. So it turns out that it worked out. I didn't think about it beforehand when I threw this thing together. But yeah, you're absolutely right. But in the case that say the two vectors weren't equal and needed to, let's go ahead and put ourselves through that pain. Okay. So again, we've got our triangle here. Said A, B, C. This is my angle that I've defined to be beta here. And if I do my law of cosines, I'm interested in this particular angle. So my law of cosines is going to look maybe a little bit funny because I'm switching the letters around a little bit. But that's because of how I've defined my individual legs. So it looks like this. When we're interested in this particular angle, the item that's squared is always the leg on the opposite side of that angle. So in this case it would be B. Then everything else on the right-hand side is just combinations of my two legs that are adjacent to my angle here. So it's going to be always be one leg that's adjacent squared plus the other leg that's adjacent squared minus 2 times one of the two adjacent legs times the other adjacent leg times my cosine beta. And I can solve this here for beta. So b squared minus c squared minus a squared over negative 2ac equals cosine of beta. If I take the inverse of both sides, I get beta is equal to just my inverse cosine of b squared minus c squared minus a squared over